This is AP Calculus BC, and in this video I'm going to talk about section 7.7, and the topic of this section is trapezoidal approximation. Your book calls it approximate integration because they go into some other things that are beyond the scope of this course, like Simpson's rule. We're going to keep it really limited to just trapezoidal approximation. So what we're doing here is we're talking about how we can approximate the value of an integral primarily from a table of values. And we've talked about this before when we were first talking about integration. We did left-hand approximations, right-hand approximations, midpoint approximations. We talked about the idea that when you have a table of data, typically a midpoint approximation is not a good idea. And so that's really what the first part of this is just kind of a reminder of what we did before. Now, when we do a trapezoidal approximation, we're doing things a little bit differently. So what we're doing is, rather than using rectangles, obviously we're using trapezoids, and we're creating the trapezoids by just connecting our data points with line segments. So you can see in this graph that I have on the screen, at the point A, I've got some value that looks like it's y naught units above the x-axis. And then when I'm at y1, I've got another point that's higher than the y naught value. It's at y1. When I connect those two together, that forms the trapezoid. Okay, so there is actually a formula for doing trapezoidal approximations, but rather than blindly remembering a formula, I would like for you to understand where that actually comes from. And to show you that, what I'm going to do is just show you how we would approximate this integral by using trapezoids. And I'm not going to write all of these out, but I'm going to write a few of them out. So let's say we were trying to get the integral from a to b for this function, and we'll just call it f of x. Well, the way that we would do that to get our approximation is we would find the area of every one of those trapezoids and add them together. So what I'm going to do here, remember the area of a trapezoid is 1/2 base 1 plus base 2 times the height. So I'm going to multiply 1/2 and my y values, that would be the bases because they're the parallel sides. I'd have y naught plus y1 times the height. That would be my first trapezoid. Now the next trapezoid would be 1/2. The bases now are y1 and y2 because those are the parallel sides, and I still have the same height because these are evenly spaced subintervals, or at least we're making that assumption. Okay, and now I'm going to continue on here, and you can see I'm going to keep using this same pattern. Now I would have y2 and then y3 times h, and then I'm going to just kind of skip along here. And when I get to the very end, I would have 1/2 of y sub n minus 1 plus y sub n times the height. Okay, so that would be the pattern I would use for however many subintervals I have. Now, what I want you to notice here is that some of these values show up in more than one trapezoid. So, for example, notice that y1 is in the first trapezoid, and it's also in the second trapezoid. y2 is in the second trapezoid and the third, and so on. y3 would be in the next two trapezoids, all the way till I get to the very end. The only two function values that don't show up in both trapezoids are y naught and y sub n. All of the other values are going to show up in two trapezoids. So if I were to sort of streamline this process, I could factor out the 1/2, I could factor out the h because that shows up in every one of these trapezoids, and then I could create a formula. And you see there's actually a formula for this. So what we have here, b minus a over 2n, that value right there is the height. The length of each one of my subintervals is the height of my trapezoid. So that's the h. And now look at these values that I have inside here. y naught shows up once because it was in one trapezoid. y1 showed up in two trapezoids, all the way till we get to y sub n minus 1 shows up in two trapezoids, and then the last one only shows up in a single trapezoid. So we can really streamline it down. Now this works when we have equally spaced subintervals. So we have this formula that's a really nice shortcut to do a trapezoidal approximation when it's appropriate. There will be times that you have data points that aren't equally spaced, and when they're not, you can't use the formula. You just have to add up all of the trapezoids like I was doing here. You would have to actually go through that process and do that. But most of the time when we have a data set at least for the sake of learning how to do trapezoidal approximation, most of the time our subintervals are going to be equal in length. Okay, so here's another representation of that same formula. This is the one that I typically use just because it's a little bit more of a simplified form. So we have h over 2 times, and then you can see y naught plus 2 times y1 and so on, all the way till we get to the last term, which is there once. And notice that the h is what we had in that previous formula, b minus a over n. That's just the length of the interval divided by the number of subintervals. So again, the key to this is we can use this formula when we have n subintervals of equal length. If we don't have equal length subintervals, then we can't use the formula. But like I said, most of the time we will be able to, but you always need to check that first. Okay, so let's just go through a few examples because this is a really, really simple idea. Okay, we've got a data set and it says use trapezoidal approximation to estimate the value of the integral from 0 to 3.2 of f of x dx. And you can see we have all these data points. Now remember before when we had problems like this, we might use a left hand or right hand approximation. And when we did that, it would essentially leave out one of the data points. And we talked about the idea that if I did a midpoint approximation, then I would throw out half or a little more than half of my data points because I have to make my intervals twice as wide. So we're going to use a trapezoidal approximation because it will use every single data point. And before I jump into the formula here, notice that these x values are all equally spaced. They're all 0.4 units apart. So that means I can use my shortcut here. So my integral from 0 to 3.2 for this function can be approximated by using h over 2. My h in this case is 0.4. So 0.4 divided by 2. And then that's going to get multiplied by, the first term would be 6.8. That would be one of the bases of the first trapezoid. And then remember, the 6.5 is going to show up in the next two. So what I'm going to do, knowing that all of these terms in the middle are going to get multiplied by 2, I'm going to have my 6.5 plus my 6.3 plus 6.4 and so on, plus 6.9 plus 7.6 plus 8.4 plus 8.8. Those are all multiplied by 2. And then I have plus, that last term is only in one of the trapezoids. So plus 9.0 just shows up one time. So again, notice the first term and the last term are there once. All of the other terms are multiplied by 2. Okay, so when I plug that into the calculator and evaluate it, that tells me that this integral from 0 to 3.2 for this function using a trapezoidal approximation can be approximated as about 23.52. Okay, so pretty simple to do. Now there's a lot of stuff you have to do on the calculator there, all very, very basic computation. The mistake most people make on these problems is honestly not the setup. Most of the time, the mistake that people make is maybe miscopying a number, typing a number into the calculator incorrectly. There's just a lot of little things you have to do, and there's a lot of mistakes that can be made along the way that are just kind of little careless errors. Now, notice the work that I showed on this problem. That's what I would expect to see when you work one of these out. Don't try to write out all the trapezoids. It takes too long. We've got a much better streamlined process to do it. The only time you would write out all of the trapezoids is if the formula doesn't work because we don't have equally spaced subintervals. Then we actually need to show every single one of them. Okay, so let's look at another one. This one, it says, use the trapezoid rule to find the integral from 0 to 3 of x squared dx with n is equal to 6. So I'm going to use a different notation this time, just so you can get used to some of the notations you might see. So remember before when we saw like L6, R6, M6, that would mean a left hand, a right hand, or a midpoint approximation with 6 subintervals. We can also use T for trapezoidal approximation. So we're going to approximate this. Now we're going with 6 subintervals. Notice we're going from 0 to 3. So my H is going to be the length of each subinterval. We're going to assume they're equally spaced here. 3 units in length is the interval. We have 6 subintervals. So my H would be 1/2. So there's my H over 2. And now I've just got to get my function values out of this. So for the first subinterval, it goes from 0 to 1/2. At 0, x squared has a value of 0. Now remember, all these terms in the middle are going to show up twice. When I'm at 1/2, 1/2 squared gives me 1/4. When I'm at 1, 1 squared gives me 1. When I'm at 3/2, 3/2 squared gives me 9/4. When I'm at 2, 2 squared gives me 4. When I'm at 2.5 or 5/2, when I square that, I'm going to get 25 over 4. And then the last term, the right endpoint, would be when x is 3, that's going to give me a value of 9. Okay, so again, notice the first term and the last term are there once. All the other terms are in there twice because they show up within 2 of the trapezoids. And then at that point, it's just a matter of plugging it into the calculator. So my trapezoidal approximation would be 73 over 8, which is the same as about 9.125. And just a really quick notation correction that I want to make here. So I said this was an approximation. When I say that I'm doing a trapezoidal approximation, I don't really have to say that it's approximately, because the trapezoidal approximation is this value. What I would use if I'm going to do that approximation is that I would say the integral from 0 to 3 of x squared dx is approximately 9.125. Okay, so it would be more correct for me to use the approximation there. When I'm saying I'm doing a trapezoidal approximation, I want to say it's equal to this value. Okay, so the question says, why is this an overestimate? Okay, so let's think about what x squared looks like. And I'm just going to do a piece of x squared here. I'm going to sketch this out. I'm not going to draw the whole thing. And I'm going to exaggerate this just a little bit. But we've got x squared, right? So let's say our first interval goes from here to here. I don't really see a lot of error. But on my next interval, when I draw in my trapezoid, notice that I've got all of this extra area here that I'm counting because the graph is concave up. So in terms of the accuracy of whether you have an overestimate or an underestimate, before when we were looking at rectangular approximations, it depended on whether the function was increasing or decreasing. When we're looking at trapezoidal approximation, it depends on concavity. So why is this an overestimate? It's because the graph is concave up. Okay, and then it also says, when could the trapezoidal rule give an underestimate? Well, that would be when your graph is concave down. All right, so the one thing you have to be careful about is this whole idea with overestimating and underestimating. If you have a function that has mixed concavities, like for certain intervals it's concave up, for certain intervals it's concave down, you may not know if it's an overestimate or an underestimate. But when your graph is consistently concave up or concave down on an interval, then we can verify whether it's an overestimate or an underestimate. Okay, so that's really it as it pertains to trapezoidal approximation. That's as far into it as we're going to go. In your book, they get into something called Simpson's rule, which is a little bit more accurate way that we can use data points. It involves using quadratic shapes between our consecutive points. But it's a little beyond the scope of this course. So you can read through that if you're interested, but it's not something that we're going to cover. So since we are kind of skipping over a lot of the material that is in the book, because they've got, the stuff on Simpson's rule in there, and they've got some things on error calculations and some other stuff that's beyond the scope of what we need to do, the stuff that's in Wiley Plus is not going to be very useful to us. So what I'm doing for this section is I'm actually going to give you a worksheet. And this worksheet is going to be your homework assignment. And what you're going to do is you're going to turn in this homework assignment via Schoology. And it's just a completion grade, but I just wanted to give you questions that were strictly on trapezoidal approximation, because if I give you the ones in Wiley Plus, they're going to have mixtures of trapezoidal and trapezoidal approximation and Simpson's rule on almost every question. And that's not something I want you to try to do. So the worksheet's here. And then at the end of this, I actually gave you the solution so you could check. So really more than anything, what I'm wanting you to do is just practice a little bit with trapezoidal approximation so that when we look at this stuff and try to implement it in the upcoming days and upcoming weeks, you'll kind of understand where I'm coming from when I talk about these approximation methods. So one last note that I didn't mention earlier is that when we do a trapezoidal approximation, it is actually the average of a left-hand approximation and a right-hand approximation. So those two rectangular approximations, if I average them out, it's the same thing as a trapezoidal approximation. And if you went through and kind of look at the formula that we did back over here, and think about doing a left-hand approximation and then think about doing a right-hand approximation and averaging them out, you can see how when I do a left-hand approximation, y naught shows up. It doesn't show up in the right-hand approximation. When I do a right-hand approximation, y sub n shows up. It doesn't show up in the left-hand approximation. So when I add up everything and then divide by 2, all these other terms show up in the left-hand and the right-hand approximation, but the ones on the end only show up in one or the other. So that's another way of looking at that formula if you want to relate it back to what we were doing previously.